Again. Hopefully we are recording now. I've got a microphone on and I'll chuck it up on YouTube so anyone can watch this over again. So this was our problem. This is our graph. We want to know which one of these statements is incorrect for this graph. Now, so far Jarrah has said he thinks it's B because the period is actually 4 pi. Can you tell me more about where you got the 4 pi from, please, Jarrah?
Because it goes to negative 2 pi and it goes to 2 pi on both sides.
Okay.
Add it together, it's 4 pi.
Who agrees with Jarrah? Who disagrees with Jarrah? Who's unsure? All right, good. We got honesty. I like the honesty. Excellent. Okay. Jarrah's put his point forward. Does somebody else like to put their point forward? What do they think is the lie? Zara?
I also think it's B, but I think that the period is pi.
But the period is pi. Can you tell us why you think the period is pi?
Because the same point, like the same point in the, I don't know what you call it, the wave, it's 1 pi everywhere.
It's 1 pi. So the same point when the wave repeats itself after 1 pi. Okay, who agrees with Jarrah? Who would like to change the vote? Who agrees with Zara? Who's still unsure? Okay, let's build on that then. This could be modelled with a cosine function. Do we think it could be a cosine function?
Yes.
Right, what's a basic sine and a basic cosine function look like? That, it does. So, normally our stock standard sine graph, I'll do it on this board because that one's not in the video. Normally our sine graph looks like this. Okay, that's my stock standard sine graph. It starts at the origin at 0, 0, and it starts repeating itself after 2 pi. And the reason it starts repeating itself after 2 pi is because that's how long it takes to do 1 revolution of the unit circle. All right? So after 1 revolution, we just go around the same path over and over again, so the graph starts repeating itself. Good. Our stock standard cosine graph looks like this. And it starts repeating itself after 2 pi, and it starts at the point 0, 1. And that's my y-axis and that's my x-axis.
So could this graph not be?
That's kind of part of the question that we're thinking about now.
Yeah, change it.
Right, how could I change the equation to change it?
You can change C.
I could change C. Where's C?
Well, put it in.
This C.
You change the equation to A cos brackets BX plus C brackets plus D.
Good. This part does what? When I have it inside the brackets. Side to side. What's the formal word we use for side to side? It's a translation. Good. So we get a translation parallel to the x-axis. And if you're ever asked to describe the transformations, we have to use this formal language. We'll talk more about that as we do more graphs over the next couple of months. All right? But this could move it sideways, so if I move this graph sideways, I could match it up with that. That is 100% true. It could be modelled with a cosine graph. All right? What about this one? The graph is dilated in both directions. What's the dilation do? Cramps it or squishes it that way, or that way. We can squish closer to the y-axis or stretch it further from the y-axis. We can squish it closer to the x-axis or stretch it further from the x-axis. This graph, our normal sine graphs go up to 1 and down to -1. Normal cos graph goes from 1 to -1. That's our stock standard no transformations graph. This one has gone up to 3 and down to -3, so it has been stretched that way, hasn't it? Absolutely has a dilation this direction. And normally it repeats itself after 2 pi. This graph repeats itself after 1 pi, so it's been squished in this way. This absolutely has a dilation. It's been squished or stretched in both directions. That is 100% true. This is our lie. You've correctly got B is our lie. But why, I'm not convinced we know why. All right? The period is one cycle of the graph. So a period is one cycle, one wave, one full rotation of the unit circle. This is one period. That's the point where it starts repeating itself. What is the period of this graph? It's not 4 pi. It is not 4. This graph, I'll put it in a different colour, is going like that. Its period is, the period of this graph is actually just equal to pi. There's a formula for calculating the period that you're supposed to know.
2 pi over B.
2 pi over B. All right, so period is equal 2 pi over B. Now this is if y equals a sine of bx plus c plus d, then it's 2 pi over B. In the actual study design for you guys, let me just show you. No, go away. I don't want to sign in. Is it really going to make me sign in? No. This is your actual study design. They don't use B and A. They are using N and A and C, right? What this part is actually doing in your study design for Year 11 Maths Methods is they're saying that your function is y equals a sine nx plus b. Was it B? No, C. So I've used the letters N and C in what I was doing. I normally, in my notes, if you see my notes or something I put up on the screen, I'm probably going to say the period is 2 pi on N. And we don't have to technically in Year 11 do too much of this transformations left and right with sine and cosine graphs. Technically it's not in the study design, but I will be doing this partially this year because it is part of Year 12 Maths Methods and I want to kind of give you a bit of a heads up. So we will look at going left and right, but it's not the primary focus in Year 11. Okay, our primary focus is having dilation, which changes the amplitude, stretches it that way. Dilation, which changes the period, squishes it and stretches it that way. And a shift up or down. So we're going to look at these parts today. And I looked at those parts in the graphing videos that I posted on Compass and in Google Classroom last lesson. All right, so the period of that graph was absolutely pi, which means that the incorrect answer, the lie, was B. Where were we up to? There we go. Okay. So what I want you to do now, think back to the last lesson, you should have done some practicing of graphing sine and cosine. I'm not convinced that you're awesome at it yet, so I want to see what you can do, could you please try and sketch this graph of y equals 2 sine x minus 1? If you need to, use your CAS calculator to help you get started. There is a grid here. Using that grid might help you. So if you want to use that grid, go from there. My big hint, if you want to make me angry, don't use the grid lines that are in your book. If you want to make me happy, use a ruler and the grid lines that are in your book. Go. Have a go.
He wanted an excuse to go for a surf, so he said it's not on his phone.
Is this right, Mr.
You're in degrees. Change. So if you go home, settings, and then in settings, change your graphing angle. Yep, so document settings. And then change the angle to radians.
Should it be on radians now?
Yeah.
It's not hard, it's excuse me, Mark. There you go, Marshall. What do you call Marshall ages?
Oh,
Martial
my
arts,
God.
what do you call him? Yeah, what do you call him? Times two.
I hate these things.
Oh, you're doing the narrative. Cool. We don't speak it.
Okay, then forward back to your current document. Okay, let's split up. Okay, those people who are a little bit stuck, I'm going to give you some hints. I'm going to show you how to do this on your calculator before I talk about how to do it by hand. So if you're nice and quiet, and if you're still working on it on your own and you feel confident to keep going on your own, do it on your own. But I'm going to hopefully give some calculator hints here. I'm not sure where you guys are at with your graphing. So first thing, home. Please, I never use Scratchpad. Scratchpad doesn't necessarily have all of the documents linked nicely together, and if I want to start using tables and other spreadsheets, then some of the data won't be connected. So if I do it in the documents at the bottom, everything links together. We set variables and formulas in different places, it's connected. So I never use Scratchpad. Okay, then I'm going to set up a few things on my graph. The first thing is when you have an exam question, you almost always get a little grid if you've got to sketch a graph. So it's useful to be able to see that grid. Menu, view, grid, lined grid. Nice. It's now starting to look a little bit better. Then I told you to sketch the graph with this grid here. So it's going up by pi on 4s, isn't it? We can set my axes to have the same thing. So I'm going to go back to my calculator. Menu, window zoom, window settings. My minimum x value was negative pi over 4. My maximum x value was 2 pi. My scale, the scale is how far apart every little grid line is. That was pi on 4 as well. And I'm going to be lazy now. I'm actually just going to type pi on 4. And my y minimum, negative 4. My y maximum was 4, and it was going up by 1s. And you've now created the grid that looks exactly like the grid you had to do your answer. So when you do get your graph on there, it's going to make it easy to transfer. All right? Second tip. Year 11 maths methods, our circular functions, we are mostly, not always, but mostly going to be working in radians. You need to be able to change your settings between degrees and radians. There are several ways you can do that. One, if you've got a newer calculator, you can actually just go up to that and click on it, and it will toggle between the different modes. Two, if you're like me, you can click on the settings, document settings, change it to radians in there. And then I also always go to make default. The reason I go make default is because it is possible to have different settings in different places. So make default. The other way, you can go home, settings, document settings, and change it.
How do I know like when to have it in radians and degrees?
Typically, if you're seeing pi's in the expression, we're in radians. And then, sorry guys, just one other thing that I know lots of people don't know this really simple trick. You've started a document, you've started working, you've gone to your home screen, it's like, how do I get back to it? Just press 4 to go to your current document. I've watched a few people start new documents over and over again because from that screen. So there's my current document. Now I can press tab, get my equation. What was I sketching? I've forgotten. 2 cos or 2 sine? There's your graph. Should look like that. Right. Now, when we transfer it by hand, let's now run through doing this by hand. First thing I'm going to do, I'm going to rule up my axes on the grid lines on my page. I'm going to label them. Makes that pi. Pi 2. All right. From a few people I spoke to last lesson, or since your last lesson when I was away, I'm not sure that you guys are very much all over this whole graphing thing, so I'm going to go through it step by step. If I'm boring you because you know how to do this, if you want to work ahead a little bit on your graphing, you can. I'll call you back in a moment. But I did create 2 videos where I go through, I think, about 5 examples of sketching graphs. They are linked onto Google Classroom, and they are also, Thomas please, they're linked onto Google Classroom. They're also linked into Compass if you want to watch them. It's my voice, it's boring, it goes for long. By all means, speed it up, double time, put it on mute and turn the captions on if you have to, whatever works for you. But if you know how to graph, that's the important thing. When I graph, this is how I do it. First thing, I recognise what's going on in the equation. So I have a dilation from x. So there's a dilation from the x-axis. This one changes the amplitude. And the amplitude is going to be equal to 2. That tells me that my graph is going to go up 2 and down 2 from its midpoint. If I had a number in here, it would change the period. So it's 2 pi over n. That number is actually 1, so it's 2 pi over 1, which means the period is just 2 pi. All right, so I'm going to get 1 revolution from 0 to 2 pi. This 1 on the end is a translation. My graph is going to go down 1 unit. So that tells me that the middle of my graph is going to be down 1 unit. When I draw these graphs, I then do like a little dotted line to show that's the middle of my graph. This is not logarithms or exponents though. This is not an asymptote. I don't label it with an equation. It's not part of the graph. If at the end you can rub it out, that's better. This line is 100% just help me draw a good graph tool. Okay, there's one more step that I take. And the step that I take is I basically work out a scale factor that I'm going to use. So to work out my scale, I'm going to take the period and I'm going to multiply it by 1/4. Which 2 pi times by 1/4 is 2 pi on 4, which is just 1 pi on 2. What this does, it shows me where every quarter of the graph is going to go. Why do I do every quarter of the graphs? Well, if we think about what a sine graph looks like, it looks like that quarter, that quarter, that quarter, that quarter. All right, a cos graph, 1, 2, 3, 4 quarters. That's basically the building blocks of my graph. So this you probably won't see in a textbook. You probably won't see on other videos that I haven't made. This is just my little drawing tip for help that I've always done since I was in year 11 to help me draw these graphs. Okay, so what that tells me is my graph is going to start normally as a sine graph at 0, 0. But it's moved down 1 spot, so I'm going to start here. That's my first point. Then my first quarter is going to go up 2 places and to that first scale factor of pi on 2. So the first quarter of the graph is going to go up 1, 2 places and to the first scale factor of pi on 2. The next quarter is going to go back down 2 places and across another scale factor of pi on 2. And then down another 2 places and across another scale factor of pi on 2. And then up 2 places and across another scale factor of pi on 2. And I create like the shape of my graph in a series of points and then just join the dots. All right. When you have had practice, you will do that much faster in an exam. Yeah? And there's lots of shortcuts you can take along the way, and when you get good at it, you're not going to do this scale factor, you're just kind of going to do these parts in your head, but you have to have the practice to become more efficient at it. All right? Okay, so this was asked to be sketched over a set domain. It is important that we show the important features. When I am given a set domain, I must show the endpoints. Must. If you don't, you're losing a mark. All right? So at 0, that's this point here. It's a square bracket, so that point is included. I have to have an open circle or a coloured in circle? It is coloured in. So it needs to be a solid dot at 0. And then I need to put the coordinates when x equals 0, y equals -1. This is an endpoint. Square bracket, so it's included, so it's absolutely coloured in. And I'm going to label it with its coordinates. When x equals 2 pi, y equals -1.
Does it affect it that you have the other dots on the graph already?
No.
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 Just as long as they end on the...
Yeah, and same thing, like if this was me, I wouldn't be drawing a massive big dot. That would just be a little marker that I made, all right? And then when I did this line, it would have been pretty faint and probably in grey lead, and I'd either just quickly rub it out or just leave it faint. Don't mark it. It was just a drawing tool, not part of the graph. When I sketch graphs, I have to show all of the important features. What were the other important features that we haven't looked at yet, Reese? Intercepts, good. Is my y-intercept covered already? Yeah. Sweet. most of the time the y-intercept will already be covered in year 11 because we haven't gone left or right. It's just part of the graph. X-intercepts, they're not covered. How do I find an x-axis intercept? Okay. X-intercept is when y equals 0. So I'm going to go 0 equals 2 sine of x minus 1. And that's about where I'm going to pause and not do any more on this graph, because this is something we haven't learnt how to do. This is today's learning intention, right? So because I was not here on Wednesday, that graphing took 15 minutes longer than it should have. But this is where we're at. This is what we want to look at. This idea of solving circular functions is one of the things that many students find pretty tricky. I'm going to try and break it down into some nice, easy steps. In the past, I've used a template. That template didn't work really well, but I'm not ready to get rid of it off the slides yet in case I decide to bring it back next year. So just ignore that that's there. I'm going to do it differently on the board. All right? We're going to look at how we solve circular function equations. Can I rub that off, or would someone desperately like, I can take a photo of it and put it up on... Well, actually, I'm going to post the video so you'll be able to see it on there if you need to. All right, so first question. What is solving? If I asked you to solve this, what are you doing? We're finding out what x equals. Good. How did we do that when we did this kind of problem? Okay, so in this very particular problem, we would have taken away 3 and divided both sides by 2. Generally speaking, how do we solve that? What do we do? Zara? We do the opposite operations. We reverse the operations. All right? So when we are solving circular functions, we have to reverse the operations. And I'm just going to jump straight into an example to help do this. So that you can see what it looks like when we reverse the operations. So we're going to solve 2 sine x minus 1 equals 0. That's exactly the problem that we were doing in the graph before. And we've got the domain. We want to find the solutions between, so we say x is an element of, this symbol means an element of, 0 to 2 pi. So we want to find the solutions for when x is between 0 and 2 pi. First thing I'm going to do, I'm going to show you how we do this with a calculator. If you got this question and it was in a calculator test, you are a fool if you do anything by hand. It's way too hard, tricky, takes too long. You're expected to just solve it on your CAS calculator. So we're going to go straight to my CAS calculator. How do I solve equations on the CAS calculator? Okay, and then we had 2 sine x minus 1 equals 0. And we want to find out what x is. And then that shouldn't have a z there. I don't know what I did. Cool? This is not going to work yet. We have to add something extra. Let me just show you what it looks like. Your calculator gives the general solution. The reason it does this is because technically this graph, this sine graph, goes like this, doesn't it? And it also goes like this way. Yeah? So when I'm asking when is it 0, it's 0 here, 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 here. You get the idea, right? There's an infinite number of solutions. So this is the calculator's way of telling me what every one of the solutions are. And all I have to do to find out what every one of the solutions are is change what this n1 is. So if I make n1 equal 0, I'll get one solution. Make it equal 1, I'll get another solution. Make it equal 2, I'll get another solution. Make it equal 3, I get another solution. Get the idea? Is yours in radians? First thing. Okay. So what I want to do with my calculator is I want to tell it that I only want the solutions between 0 and 2 pi. So I don't have to retype it, just arrow up, get to your equation, hit enter, it'll copy it down. We're going to add a given statement. We're going to define the domain. To do that, I'm going to go to the little blue parts above the equal sign, so control equals. And then I want to use this vertical line. This vertical line means given. All right, have you seen that before?
Yeah.
Good. Good. Yes, so you set the domain. So we're going to do exactly the same. We're going to set the domain. So given that my domain control equals, so we're going to tell it that x has to be between 0 and 2 pi. Now it gives me two very specific answers. All right. When are you going to use your calculator to do this type of problem? Whenever you're allowed to. If you're allowed to use your calculator, don't waste time doing it by hand. It's not worth the marks. All right. So, solving circular function problems, we need to set a domain, otherwise you'll get this ugly thing that includes every possible answer that's available. But we do have to do it by hand sometimes. I'm so over time. So let's look at how we do it by hand. Oh, let's change my colour scheme going on here. Is the green okay for step 1? Right. Is the green still okay? Can you read it? So we're going to do the initial solving part. We're going to get sine or cosine by itself. So in this problem, I'm going to add 1 to both sides. Let's do it in the black, should be okay. So I moved 1 to the other side. And then move the 2 to the other side. How do I move the 2 to the other side? I divide both sides by 2. Yeah? Still with me, Thomas and Marshall? No. Right, tune in. No. If you don't want to tune in, you can just leave. All right. Okay, so I get to this point where I get sine by itself. Then what I'm going to do is step 2. I'm going to find my reference angle. And this comes from the exact values table. And that is exactly why I drew it on the board before I came in today. So what we're asking is when is sine a half? Okay, when is sine a half? What's the inverse of sine? What's the opposite of sine? When is sine equal to a half? I go to my exact values table, I find a half, here's sine is equal to a half. What angle gave me sine is equal to a half? 30 degrees, or we're working in radians, pi on 6. I'm going to try and work in radians because the question was in radians, okay? So my reference angle is pi on 6. All right, step 1, step 2 covered. This won't always be one of your solutions. I'll talk more about that when I do a different example. Step 3. We're going to draw the unit circle and locate the solutions.
In the test, are you allowed to draw just part of the unit circle? Like just one quadrant?
Well, actually, it's not going to be helpful for me to draw one quadrant. You can, you don't even have to draw it, but I'm going to show you why I'm going to do both or all quadrants. So what I've got to think about here is we're going to go back to my unit circle. And then we're going to think about this problem here. And this problem says, when was sine equal to a half? If you've got to go, you've got to go, it'll be recorded. When was sine equal to a half? Okay, sine is what? The horizontal or the vertical level? Vertical. So sine is a half about here, yeah? That's when the vertical height's a half. And this is my solution that I have already found from the exact values table. That was pi over 6. But this one over here is also a solution. And that's why we've taken our reference angle and we have located where the solutions are. There's one here and there's one over here. This one will be 5 pi over 6. And that's why we practice finding those angles in the unit circle and why we've got it stuck into our summary journal to try and memorise it. And why I said it's good if you memorise this, because if you're doing it by hand, you're not allowed your calculator. What are you also not allowed? Your summary journal. We've got to memorise where these things are. Or we've got to be able to work out where they are. Okay. So this is the location of my two solutions. Then, step 4. We're going to use the domain to find all solutions. All right. Now, in this one, we're actually already done because our domain was from 0 to 2 pi. So if we track around in our unit circle and we go from 0 and we start travelling around our unit circle, we get our first solution. X equals pi on 6. And then we keep cruising around our unit circle. We've got our second solution. We still haven't gone 2 pi yet, have we? 2 pi is 1 full revolution. So we've got our second solution. We keep going around our unit circle. We're not finding any other solutions and we get to this point that's 2 pi. We have found all of the solutions. We're done. All right? So we've gone around the domain. We've found out where all of the solutions are. This is our answer. It links with what we did on the calculator. Nice, good. We're starting to match up. Did it pretty slowly though, didn't we? Yeah. We would be expected to do that. We'd be expected to do all of that in probably 2 to 3 minutes, right? So we're gonna have to try and do a bit of practice to get a little bit faster. So let's do a little bit of practice to try and get a little bit faster. I'll give you a moment. There's a couple of pens still waggling, writing stuff down, so I'll let you write that down. Those people who are doing the retest, it is a little bit shorter. I want to go through at least one more example before I start you on the retest, all right? Does anyone have to leave? If we went a couple of minutes into lunchtime, would that be the end of the world? No? All right, I just would really like to do one more example. Yeah, well, you probably should. Okay, let's do the second example. I'm going to keep the green bits because they're going to be our steps. Except now I'm going to have a go at, which one do you want me to do? Don't say that one. Out of those two.
Bottom one.
Third one.
Cos x plus root 3.
Right, let's do this. So we want to solve cos x plus root 3 equals negative cos x, and we want for x to be an element of negative 2 pi this time to 2 pi. So our domain's changed. All right, domain's changed. Okay, so first step, we're going to complete the initial solving to get sine or cosine by itself. So we need to get these cosines together. All right, how would you do that? I would add a cosine to both sides. Happy with that? So that gives me 2 cosines plus root 3 equals 0. And then now I would do my rearranging like in the last example. 2 cosine would equal negative root 3. And then 1 cosine would equal negative root 3 over 2.
Couldn't you just divide both sides by cos?
No, because then that cancels out the coses and it cancels out your x's and it gets ugly. You don't want to eliminate a variable that way. You would, if you ended up with like multiple coses in there somewhere, you would use factorisation and then the null factor law. That comes up, that's a higher level problem. All right, from here, we're going to find the reference angle from the exact values table. Now, we don't have a negative root 3 on 2 in our exact values table, do we? No. So what we're actually going to do, we're going to find our reference angle, and we're just going to do inverse cos of just root 3 on 2. We're going to ignore that negative. All right, so we'll go to our exact values table. Where does cos equal root 3 on 2? Here. What angle gives cos to root 3 on 2? In radians? Pi on 6. So my reference angle is pi on 6. My answers will have something to do with pi on 6. Okay, let's draw the unit circle to locate where these answers are going to be. Okay, beautiful unit circle. Not my best circle, we'll deal with it. This is where I bring the negative back in here. We're saying, okay, cos has to be negative root 3 on 2. So where is cos negative? Is cos vertical or horizontal? Horizontal. So cos is horizontal. So where is cos negative? It's in the second and third quadrants. So cos is negative over here. So we want cos to be negative root 3 on 2. Negative root 3 on 2. So that's going to be 2 points there. And I haven't drawn it well. I'm actually going to change that a little bit because it almost looks like it's pi on 3 and I just don't want to create confusion. It'll be a little bit further along here. So 1, 2 spots. And they have something to do with pi on 6, don't they? Because that was my reference angle. Yeah. So this one has something to do with pi on 6, but that's not pi on 6, is it? That one has something to do with pi on 6, but it's not pi on 6. What's this angle that has something to do with pi on 6s?
5 pi.
That's 5 pi on 6, good. What's this angle that has something to do with pi on 6s? 7 pi on 6. Right, we've located where my two solutions are. Now we're going to use the domain to find all of the solutions. So let's start at 0, and we're going to go round the unit circle. We're going in the positive unit circle direction, and we get to our first solution at pi on 6. Sorry, 5 pi on 6. And then we keep going around the unit circle, and we get to our second solution at 7 pi on 6. And then we keep going around the unit circle, and we get to 2 pi. So we've finished in that direction, haven't we? But what we didn't do was go to negative 2 pi. So how am I going to do that? Well, I go backwards. So I start here, and I'm going to go around the unit circle. I get to this point. This won't be 7 pi on 6 anymore because I'm going backwards. This angle will be minus 5 pi on 6. And then I keep going around backwards, and I get to this one, and we get minus 7 pi on 6. And then I keep going around the unit circle, and I get to negative 2 pi, and I'm done. So I actually have 4 solutions. Right, here's the kicker. The way I showed you to do this is using the unit circle. There are lots of different teachers who do this part quite differently. One of the other methods is you can just add and subtract the period to find all the different answers. There's another method where you use the graph, and if we had the graph, we can work out how many solutions we need. As we work through this unit, your goal is to try and determine the way that you like best for finding all of these solutions. And when we get a little bit further into graphing, you'll have a better idea of which way you like to do it, and I'll have more opportunities to show you different ways. But I reckon this video has been going for about 50 minutes already. So what I would like you to do is to actually have a go at some solving equations questions. I think they're in exercise 4G, 14G. Can someone please just check that I had the right set of questions here? That looks good? Okay, so what's going to happen is I'm going to stop the video. The people who are practicing this skill, you can go on to exercise 14G and do some practice questions silently. The people who are doing the retest, I'm going to put you on a table on your own and you're going to work on the retest. But what I have also put in to Google Classroom, if you go to Google Classroom, you go to classwork up the top, and it updates. Try that again. Perfect. Sorry, guys, can you just grab a seat? Let me show you where this is. With me? With me? Google Classroom, go to Classwork. Scroll down to the circular functions topic. I've added some material in here, so if you go circular functions, support, videos and notes, there's a link to a video on sketching sine and cosine, link to a second video on sketching sine and cosine, and I have created a neat set of worked examples for those 3 worked examples that were on the slides with some annotations that you might like to follow through, or if you're doing the test now and you want to come back to this at a later date, that can be there to help you. All right? If you choose to print this off to add to your summary journal, that is okay, but the expectation is that you add your own annotations to it. If you just print it off and stick it in, it's my work. If you print it off and stick it in and add annotations, you've made it your work. That might save you some time with your summary journal entries. Right, I'm going to shut up so that we can get on with the lesson. Thank you.